Number 2 is exploring not a reaction that we've done, but it's certainly exploring a concept that we've done before in lab. So a reaction took place and they clearly collected the gas over water. This was the total pressure of the gas that was collected over water, and they say the vapor pressure of water is 30 millimeters of mercury at that temperature they collected it at. And you remember that, so the total pressure 755 is for all of the vapor in here, including the water. So in part A, they want to know what is the partial pressure of the oxygen gas that was collected. And so the oxygen gas is represented by the black dots, the water is the blue dots, and we need to subtract out that little bit of pressure that's due to the water. So that should be pretty straightforward. All we have to do is go 755 millimeters of mercury minus our 30 millimeters of mercury, and our answer should be 725 millimeters of mercury. Check for sig figs because it's a numerical answer, but remember we're subtracting. This one went to the tenths place, this one went to the ones. Ones is not a specific, so our answer should go to the ones. So that should be the answer for A. In B, they want to know how many moles of oxygen gas were collected. Well, we have lots of gas law information. One is we just found out a moment ago that the pressure of the oxygen in the flask was 725 millimeters of mercury. We also know a lot of other things. We know the volume, I should say V, right there. We know the temperature, which we could convert to Kelvin. We know the pressure, and we know everything we should in order to solve for moles in our equation. So I've done a few things here. One is, remember we need the pressure in ATM, so I converted my pressure to ATM, remembering that there's 760 millimeters of mercury per atmosphere. Our volume was already in liters, so I already plugged it in, and our temperature I had to convert to Kelvin before I used it. Remember that R is 0.0821 in this case because it's a gas law problem and there's no joules involved. And what I got for N here was 0.0557. And let me think about sig figs here. We had 3. We still have 3 here. That was 3. I think 3 is probably going to be the appropriate number here. So 0.0558 moles of oxygen. That's sloppy, but we'll box our answer, and we checked our sig figs. In part C, they want to know what would be the dry volume of oxygen gas at a pressure of 760 and a temperature of 273. Now remember, there's nothing mysterious about dry volume. They're just saying that this originally was not a dry volume. In other words, we hadn't subtracted out the water vapor yet. So when we subtracted it out and got 725 millimeters of mercury, that was a dry volume. So alright, they're saying if this was our starting dry volume, our starting pressure of oxygen, what would how would the volume change if we increase the pressure to 760 and change the temperature to 273? So the temperature is going down. So there's more than one thing changing here. So our ending values, we're saying we want to know what the volume will be after these changes. The pressure is going to be 760 after the changes, and the temperature is going to be 273 after these changes. And so this is a classic situation where we need the combined gas law, especially because we're changing more than one variable. And you remember when you're doing the combined gas law, no longer is it required that we have the pressures in ATM because we don't have R in there. We can keep it in millimeters of mercury. As long as we're using the same units in the beginning and the end, we'll be fine. So I've plugged in our values here, the starting pressure, the starting volume, the starting temperature, and the ending pressure, the ending volume, and the ending temperature, divided by 760, multiplied by 273, and I'm about to write down the answer, and I was thinking about sig figs here. They're being a little bit mean. You might think, well, okay, so it's going to be 3 sig figs just like it was in the beginning. That usually is a pretty good approach. But I noticed this 760 only has 2, and I double checked, and there is no decimal. It's kind of a mean thing to do, but I think there's only going to be 2 sig figs here, So I get 1.2, and then if you're thinking about what units, well, you remember the volume in the end is going to be the same as the volume in the beginning, so it's going to be liters. And that's our answer. In part D, they want to know what mass of potassium chlorate was consumed in the reaction. So I read you the reaction down here from the top, because this is a stoichiometry reaction. Remember that we found out in part B that it made 0.0558 moles of oxygen. And that must have come from this stuff doing the reaction, right? This was decomposing as you heated it, and it made this gas. So all we got to do is start here and go back and find out how many grams of this stuff it came from. I'm going to do a train track, but of course you could do a before and after diagram if you wanted to. Alright, so here's my conversion from moles, doing the mole ratio back to KClO3, and then just the molar mass of KClO3 to get back to my grams. I'm going to do 3 sig figs here. You know, you should never limit your sig figs based on your molar mass. Always add it up so that you've got enough. And this, we determined there were 3 sig figs back in problem B, so we should use the same here.